Okay, so welcome to the course. So last week I announced that today I would spend first hour on the last topic we were discussing, and then on the second hour I was going to answer your questions. But then I decided that the lecture I was going to explain will not be included in the exam. So in this case I will skip that part, and instead I will spend entire 2 hours on your questions. Okay, so let's use this 2-hour period for a general review of the course, and hopefully you will all have your questions cleared during these 2 hours, and you will feel much better for the exam. Okay, so how should we start? So since we have 2 hours, if you want, I can go over each and every question. Do you think is that a good idea? Instead of taking questions from each one of you. So let's do that, right? So let's starting from the very first exam. Okay, so this is the second midterm from 2010. Okay, I think you have the answers to all questions here, right? That's what it looks like. Okay, so let's start from the first one. Okay, so the first question just asks about the standard atmosphere tables. So I don't know what's written here, but probably everything you need to know about standard atmosphere tables are already explained here. So I don't think there's anything else I need to say on top of what is written here. Okay, so I'm just skipping to the second question. Okay, so in the second question it says explain thrust required, power required, thrust available, power available, and specific excess power. So, so specific excess power is not included in this exam. We haven't seen that yet. So you should just forget about the last part. But the first 4 things are really important to understand, because I know that most students are confused about these things. What is thrust required and what is thrust available? And once you understand those, power available and power required are basically the same thing. But you should really understand the difference between thrust required and thrust available. Okay, well, there are 2 things I say, but there's a sentence I say for each one, thrust required and thrust available, to make you understand the difference. First of all, thrust required is entirely related with the design of your aircraft. Okay, so thrust required is simply equal to the drag force, and everything that affects the drag force on an aircraft affects thrust required, and it has nothing to do with the engine. Okay, so here this is a very good example. You see 2 aircraft here. They are both F-16 aircraft, but the first one here is a clean configuration. Okay, let's see. So this has a certain amount of drag force, but if you look at the second one, a lot of additional external loads are attached to the wings. So each one of these loads contribute to the aerodynamic forces, and their contribution to the lift force will be very minimum, but they will have a significant effect on the drag force, right? Because if you look at the front view, you see that the area that is exposed to airflow is much larger, and hence there will be a much greater drag force. So if you compare the thrust required values of these 2 aircraft, this one should be significantly higher due to these additional aerodynamic surfaces. Okay, so again, this has nothing to do with the engine. It's only equal to the drag force. Thrust available, on the other hand, is the actual thrust force created by the engine. And the thrust available is all about the engine, because it is created by the engine of the aircraft, and it has nothing to do with the aerodynamic design. So while these two aircraft have different thrust required values due to these additional attachments to the wings, they have the same thrust available if they have the same engines, okay? So which normally they should, right? So if you assume that these aircraft both have exactly the same type of engine, then they should produce same amount of thrust force regardless of the thrust required, okay? I don't know is this clear? So do you have any confusions about the difference between thrust available and thrust required? Okay, so thrust required changes with speed. Well, it changes with other factors as well. Since thrust required is equal to the drag force, anything that affects drag force affects thrust required. So aerodynamically, it certainly depends on angle of attack, because if you are flying with a low angle of attack, then the lift coefficient will be less, and since the drag coefficient depends on the lift coefficient through the drag polar relation, the drag force will be less as well. But if you increase the angle of attack, then drag force will be increasing. That means the thrust required will be increasing as well. If you remember our thrust required curve, we plot thrust required as a function of flight speed, and this thrust required curve is valid for a steady level flight condition. Okay, so thrust required curve is formed by a number of points, and every point on this curve corresponds to a steady level flight condition. Okay, so for example, let's pick a point here. Let me just mark this as red. So for example, if you consider what's happening at that point the aircraft is making, let me call this V1. So this point corresponds to a steady level flight condition. At V1, at speed V1, and at an altitude where air density is rho. So that means these two equations should hold for that condition. Thrust is equal to drag force, and since weight of the aircraft is known, from here we have 1/2 rho v squared. This is V1 S times CL. So from here we conclude that this aerodynamic lift coefficient CL has to have a certain value, which is 2 times the weight of the aircraft divided by rho times V1 squared times S. Okay, that means the drag coefficient has to have a certain value, which comes from the drag polar relation. Okay, and so instead of writing, let me just type it. So that means the drag coefficient has to have a specific value as well, which comes from the drag polar relation. Thrust required is then equal to the drag force obtained from the drag equation, right? Which is thrust required is equal to the drag. That's equal to 1/2 rho V1 squared times S times CD. And this CD that corresponds to this CL. So this is CL. Okay. So this is thrust required. Thrust available, on the other hand, depends on the type of the engine and how much fuel is supplied to the engine. And the fuel supplied to the engine is controlled by the pilot. Okay, so the pilot has a throttle lever in the cockpit, and he chooses how much thrust force he wants to give to the engine. So by changing that throttle position, he can adjust the amount of thrust created by the engine. So let's say that the aircraft is flying at this point, right? So this should be a steady flight condition. That means whatever the thrust required is, the same amount of thrust should be supplied by the engine. Okay? So if this is let's say this is a jet aircraft, then for jet aircraft, this much thrust force should be provided by the engine. And if it's jet, then I was going to say that the thrust force doesn't change with speed, but I'm afraid that may confuse you. So anyway, so the pilot should adjust the throttle such that he gets this amount of thrust force from the engine, so that he can continue this level flight condition. So the speed and altitude will not change. So what happens if the pilot changes that? Suppose that this corresponds to, I don't know, 50% throttle. Okay, so all of a sudden, let's say that the pilot increases the thrust force. In that case, there will be more thrust provided by the engine compared with the drag force, and it will not be a level steady flight condition anymore, right? So we will consider that case as well in the future. But so far, we are only interested in steady flight conditions. So if the pilot gives more thrust force than the drag force, then this will not be satisfied anymore, right? So in that case, the thrust force will be larger than the drag force, and that means something will change. The first thing that comes to mind is the speed of the aircraft. If you provide more thrust force, then there will be a forward net force, and that will cause an increase in speed of the aircraft. But again, for now, we are only considering the steady flight conditions. So in this case, we always assume that whatever thrust created by the engine is should be equal to the drag force of the aircraft. Okay? So everything I said about thrust available and thrust required can be translated to power required and power available. The only difference is when you're talking about power, you should know this relation. Power is equal to thrust times the speed of the aircraft. So you just have an additional speed term added to your equations. But other than that, the available versus required concepts are the same for power. Okay? Is this good? Do you still have any questions about available versus required? So this just comes from physics. It's not something new specific to this course. Okay. So there's a question about the determination of the maximum speed of the aircraft. Okay, so let me come back to this. So let's say that the aircraft is flying at this point, right? the thrust force created by the engine is equal to the drag force, and let's say this corresponds to 50%. Okay. Suppose that the pilot gives full throttle. So all of a sudden, engine starts creating much more thrust force than drag force. So as I said, then this equation will not be valid at first. So there will be an acceleration. Okay, so the aircraft will start accelerating. So the thrust force will be larger than the drag force. But as the aircraft accelerates, the drag force will be increased as well, since it is proportional with the square of the speed, right? So as the speed of the aircraft increases, the drag force will be increased as well, and this will continue until they are equalized again. Okay. So the drag force increases all the way up to the new thrust force, and at that point there will be a balance again. The thrust force will become equal to the drag force at a new speed. Okay, and if the altitude is kept constant during this acceleration, then they will come to a balance at a new speed. Let's say, so this was the thrust force at 50% throttle, and if the thrust at the full throttle is here, the aircraft will accelerate. It can accelerate only up to a certain point, and at this point the thrust force at full throttle will become equal to the drag force, and this will be the maximum speed of the aircraft. It cannot really fly any faster, because if it does, then there will be inequality again, right? There will be this condition where the drag force will become larger than thrust force, and it will slow down the aircraft. So this is TA max. So at this point, the maximum speed of the aircraft is found. Okay. Okay, so I'm moving to the next question, if you don't have any other questions about this. Show that for minimum thrust required for an aircraft at steady level flight, this condition should hold. The induced drag coefficient should be equal to the parasite drag coefficient. So I did this in class before, and the derivation is given here. So I guess I don't need to talk anymore about this. But let me ask: are there any questions about this derivation here? Okay, so let's see how we did it here. Well, actually, there are two ways this can be shown. This equality can be shown. Here I wrote the thrust required in terms of lift coefficient, and then I differentiated it with respect to the lift coefficient, and from there I arrived at that condition. But we can do this in another way. Let me show that as well. So another way to prove this is, so let me just type again, because I plan to say a few things here, and it will be easier if I just type. Another way to prove this is to write the thrust equation as a function of speed, and then do the following. You basically do the differentiation with respect to speed. you take the derivative of trust required with respect to V and then equate that to 0, you still get the same thing, CDI is equal to CD0. Okay. So let's see what else we have here. Oh, this is a good one. It says show that the minimum thrust required does not depend on altitude. Okay, so we know that at minimum thrust point, this relation should hold. That means when the TR is min, we have, when we call it V star squared S times CD, and CD is equal to CD0 plus CDI, but this is equal to 2 CD0. Okay, so you should really be careful here. If you just do this and leave it at that, that will be, so these twos will cancel and you'll be left with rho V star squared S times CD0. So if you look at this relation, you see a rho term here, right? So that may give you the idea that it does depend on air density because you have rho in the equation. But that's not really true because you don't know what this V star is. So V star has a special value. Okay, so let me just put my plot here. So V star is here where that becomes minimum, and the vertical axis is the minimum thrust required. This is TR min. So again, if you just look at this equation, you get the idea that TR min depends on rho. But again, the V star has to have a special value. So let's figure out what that special value of V star is. That special value of V star can be calculated from the lift equation. S times CL. And CL has to have a special value as well, which comes from this relation, CDI is equal to CD0, but CDI is equal to K times CL squared. So from CL is CD0 over K, and you take the square root of that. Okay, so from here we found the value of V star, which is, actually I can just write it square, 2 times weight divided by rho times S times CD0 over K. Okay, so next I take this and then insert it here. That gives me and we are left with this thing, 2 times weight okay, so when you get rid of the V star term, you see that the rho term disappears as well. And if you look at this final expression, all of the parameters in this relation are constant numbers. Okay, so weight of the aircraft is a constant number, and K is related with the drag polar relation, so that's a constant number as well. So everything here is constant, and you conclude that the minimum thrust required is given by this relation. So it changes if you change, for example, the weight of the aircraft. Okay, so if all of a sudden the aircraft drops some cargo, in which case weight will change, and if you look at this expression, the minimum thrust required will change. But other than that, it doesn't change with altitude. If you climb to a different altitude, then air density will change, the rho term will change, but this will stay constant, okay, since there's no rho here. Şunun mu? So you have a square root of CD0 on the denominator and CD0 here. Okay, so if no further questions, let's move on to the next question. Okay, so in the next question, it asks you to show that for the minimum power required, the condition is different. The idea is the same. You again write, instead of thrust required, you write power required, and you do the differentiation with respect to either CL or V, and then equate that to 0. Since you have an additional V term here, when you take the derivative, things change, right? And as a result, you get this condition. The induced drag coefficient should be 3 times the parallel drag coefficient. In the second part of this question, it says find the dependence of minimum power required on altitude. I don't think I need to go through this because the idea is the same. If you do that, if you do what we did for thrust required for power required, you will see that there will be a rho term left. So for thrust required, the rho terms cancel each other out. So this rho cancelled the rho here, and both rho terms dropped out. But if you do that for the power required equation, there will be a rho term left, right? And that's because you will have a third power of V here. So this is, if you write this for power required, you will have a third power here, and that third power means that you will have rho to the power 3 over 2, and hence the rho will not disappear completely, and you actually see the result here. So in the final expression, you have this square root of rho left here, and it says that the minimum power required is proportional to, or inversely proportional to, the square root of rho. Okay? The fifth question is related with the climbing flight, which we haven't seen yet, so it's not relevant for this exam, so we can skip that part. Similarly, the sixth question is, let's see, no, this is related with our course, I'm sorry. Okay, it says that consider a jet aircraft with the following properties. The aircraft is cruising at 4,000 meters with 60% thrust force, and it says that find the cruising speed for this condition. And I say here I am asking for the larger one. And the solution is already here, right? I'm not sure if I need to elaborate more on this one, but let me. So the information of the aircraft is given. Using that information, we can find the expression for the thrust required curve, which will be something like this. And it says that the aircraft is cruising at 60% thrust. So we know that the maximum thrust is this much, and we need to adjust the thrust to 60%. And this is a jet aircraft, so thrust should be fixed. So if the full thrust is this much, so this is 100% TA max, then 60% will be 6% of that. and from here the cruising speed can be found here. So the reason here I say that I'm asking for the larger one, you can find a second speed which is this one here, but that's not what I was asking in that question. So I asked you to find that number. Okay? And the solution is here. If you want to see what the actual number is, you can just go through that. Mm-hmm. Mm-hmm. Olur. Yeah, you can use that formula directly, but I really don't want that because that formula for speed comes from the solution of the equations. Okay, so if you try, you can memorize that formula, but there's no need to. If you know the basic equation, you can come to the solution yourselves. But if you already know that, you can apply it. Part B is again related with the climbing flight. So I'm skipping this question. And there's part C. Well, to be able to answer this part, you need to know how available thrust and available power and required thrust and required power changes with altitude. I started talking about them, and I was planning to continue today, but then, as I said, I decided to exclude that topic from this midterm. So this question now is irrelevant for our midterm that we will have on Thursday. So let's skip this one. Again, the part D is not related. So let me just skip that as well. And finally we come to the seventh question. And the seventh question is totally excluded from this course. I will not talk about ground roll at all. So you will not learn how to answer this question. Well, the solution is provided here, but this year I'm not going to talk about this topic. So anyway, I think this is all I can say about this midterm from 2010. And if you look at these questions, you should realize that the course was much more involved back in 2010. So it's much more simplified now. I mean, if I look at these questions, and especially this question was really hard. This question, which is fifth question, I think. No, the sixth question. So this is a very complex problem, and even after I explain the climbing flight, this question will still be a very, well, I shouldn't say very, but not straightforward. It requires some thinking to solve this question. So anyway, you don't have to worry about it for this midterm. Okay, so let's take a look at the next sample midterm from 2011. Bunun çözümü yok galiba, var mı? No, it's just solutions here. What is that? Only for one of them, one of the questions. Okay. Well, the first question is the same. So let's move on to the second question. So this was again the same question from the previous exam. So in the second part, it asks to draw a force diagram for an aircraft making a steady climb. Again, not relevant for this exam. So the third question, steady level flight at a given altitude, explain how the maximum excess power can be computed. Again, excess power is something we haven't seen yet, so the third question is irrelevant. So let's come to this fourth problem. So we have propeller aircraft with weight given, S given, and the maximum available power given. Just find the maximum rate of climb and speed at which. Well, unfortunately, this question is not relevant for this exam either, right? Well, except that maybe you can. That's right. The part C is you can do that part, right? Find the minimum thrust required speed. So this is very easy, right? So can everybody see how to answer this part? Find the minimum thrust required speed. Efendim? Bilmiyorum ki, ışığı biraz kapatsak daha mı iyi olur acaba? Okay, so actually there's something I need to say about this problem. I'm only talking about the last part, part C. We are asked to find the minimum thrust required speed. So we are asked to find this V star value. Well, if you already know that for this condition CDI should be equal to CD0, you can directly use that. But if you don't, that's still fine because you can drive this condition from scratch, right? But either way will be fine. If you already know this condition, then you can just go ahead and find the result as follows. K times CL squared is equal to CD0, then CL is equal to CD0 divided by K square rooted. And then you insert this into the weight equation and that will give you the speed, right? So this is known. S is given, rho is given, weight is given. The only unknown is V star, and you can just solve for V star from this equation. And again, if you didn't know this condition, then I would expect you to derive this condition first and then find the answer as shown here. Okay? Doğru. So that's a very good point. So as your friend says, for the minimum thrust required, we know that lift to drag ratio should be maximum, and you can approximately get that from the that's true. To be able to find the answer, you need to know these values, right? CD0 and K, which are not given, are they? No, they're not given. You are only given the this drag polar curve. So I think that was the tricky part about this question. So you need to find these values first, or instead of doing that, you can use this relation: TR is equal to weight over CL over CD. And then TR min is equal to weight over CL over CD max. And CL over CD max can be obtained from the curve. So you just draw a straight line. So it looks like they will be tangent at this point. So it's very close to 0.04. And the lift value is this much, 0.6. So the maximum ratio is the ratio of the two, which is 15, I guess, right? So from the graph, you read the maximum ratio is approximately 15, which is a good enough number. So by the way, most probably there will be questions like this where you will need to read data from a graph. So in that case, it is okay if you can just use an approximate number. I mean, so if, for example, if you do this and you say that they seem to be tangent at this point, so this is the closest one. So let me take it as 0.04 and it will be a valid answer. Okay? So don't worry about trying to be too accurate. Well, in most cases, when I ask you a question like that, I try to be very careful, and I give you very easy to read points. So if you look at the graph carefully, you will see that easy to read points, and most probably those points are related with the solution. So instead of doing that, you can find K and CD0 values, and if you try to do that, it will be easier for this case because so this is 0.02, this is equal to CD0, right? And for finding the K, you can use this point, for example. So obviously this point is at 0.08 and 1, and if you use that point, you say 0.08 is equal to 0.02 plus K times 1 squared. So from here you get K as 0.06. So again, when you see a graph like this, just take a look at it carefully, okay? Because I give you nice points that you can use directly, such as this one. Okay, so let's give a break and continue after the break.